maybe a more provocative way of phrasing it is that you can take the point of view that you want to eradicate bias, you want to be super objective, but sometimes it's wiser to just accept that humans are biased inherently, in the sense that we have individual preferences which drive us to spend, put our energy into some things and not put them into other things. And try to say that if you have enough people, a diverse enough collaboration with a diverse enough set of preferences, then on the aggregate, actually, the collaboration as a whole is not biased, even if each of the individual members has things that they deeply care about.
Hi everyone, I'm Balázs Kegl, and this is the iScientist podcast, where we explore artificial intelligence, science, and the scientists behind the science. So I'm so excited today to host Vava Gligorov, my good friend, an experimental physicist who I met 10 years ago maybe, when I was working with experimental physicists. So hi Vava, how are you today?
Hey Balázs, no, it's I'm great. I just came out of actually my PhD student just defended his thesis a few hours ago, and I'm super excited because you and I haven't. It's been a long time since we had a chance to really chat. So yeah, looking forward to it.
Yeah. So let's start. So Vava is an experimental physicist, and when I actually started to work with experimental physicists, it was strange to me because I knew theoretical physics. I thought physicists were these math types who, like Feynman, at the blackboard writing a lot of equations. But experimental physicist is like a completely different animal, and Vava is especially the doer type. So experimental physicists actually do stuff. They build the detectors, they build the experiment, they are the engineers. And if you want to know, if you've seen Oppenheimer, there was a scene in it which was exactly explaining this, where they wanted to give the task of making sure the bomb works, the engineering, to Ed Teller. And he was like refusing it right away, and they just forgot it. They give it to Fuchs, who happened to be a Russian spy, by the way. It's another story. Not to say that Vava is a Russian spy, but that was pretty funny. So Ed Teller just went back to the blackboard, doing his calculations on the hydrogen bomb, and never really touched, the engineering of it. So experimental physicists are really the people who are doing the stuff. And Vava is not only doing it, but he's inspiring others to do it, because he has a team. He worked on the trigger of the LHCb experiment, which we will explain later, and also on the upgrade of the LHCb experiment. And so one of the problem, of course, in experimental physics, that you never get the Nobel, right? Because these are huge experiments.
And somebody out there is playing the world's smallest violin for our pain, but indeed, that's not the game.
So yeah, so that's the sacrifice you.
We're collectivists by nature.
Exactly, and unfortunately, I think there should be a possibility to give the Nobel Prize to collaboration, but so far it hasn't happened. Yeah. In any case, so first question, I would like to ask you a little bit what you do. Just give us enough explanation, so then we can explore your journey to arrive there. Why you became a physicist and how you became a physicist. So tell us what you do. What is this experiment you work on, and how it works?
Right. Okay, so what I do and what is the experiment I work on? Let's begin with the experiment. So in the simplest possible terms, right? One of the outstanding questions that we have currently in fundamental physics relates to the beginning of the universe. So we have a theory which we call the Standard Model, which describes the fundamental constituents of nature, fundamental in the sense that they don't have any internal structure. So an atom is not fundamental because it's made out of protons, electrons, neutrons, other things. But a fundamental particle, something like an electron, it doesn't have things it's made out of. Okay, so we have this model has a total of 17 fundamental particles, and they're sort of all of reality, if you want, is built from those building blocks. Now, at the beginning of the universe, our best theory, if you want, we have the microscopic world and the macroscopic world. So the particles are the microscopic world, but then the macroscopic world, you know, galaxies, stars, etc. It's actually an interesting question conceptually whether that has to how you get the macroscopic structure from the really small. At the beginning, though, our current best theory is that we had the Big Bang, where essentially the current universe came out of a very microscopic, dense energy collection of energy. And when you create matter out of energy, in principle, you should create equal quantities of matter and antimatter. Antimatter is just like matter, except that it has opposite electric charge. So every fundamental particle has its own antiparticle. The antiparticle will have opposite electric charge, if the particle has an electric charge. And when you bring them into contact, they annihilate. And now, the thing is, you can ask, okay, so if my universe was created as equal parts matter and antimatter, where is the antimatter? Obviously, or the matter, because the convention would recall what, right? And you can convince yourself very easily that there is no antimatter in the universe by looking at the sky at night, because if there were regions of the universe which are made of antimatter, they would come into contact at some point with regions that are made of matter, and they would annihilate, and you would see, you know, flashes of light and so on, and that just isn't there. Of course, there are many more sophisticated ways to reach the same conclusion, but that's fundamentally where it's at. And so we have to understand the standard model of particle physics, so as I say, our best theory of the microscopic, admits that there are some differences in behavior between matter and antimatter, but those differences are not even close to big enough. So we're talking 11 orders of magnitude, even close to big enough to cause that the antimatter just goes away. And so that leads to the question, what happened? And is there some additional physics beyond this current theory? Okay, which is the cause of this? That's like the fundamental question. And then my experiment, LHCb, is a detector. It's about 20 meters long by 5 by 5 in the other two directions, roughly speaking, okay. Has about 1 million electronic channels, again, roughly speaking. And it's designed to help answer this question by making very precise measurements of the behavior of matter, behavior of antimatter, and understanding how those measurements compare to the predictions of this so-called standard model. And that's so that's like the mission, the big mission statement. Now, this is an experiment to give you an idea of the timescales. This thing was proposed in the early 1990s, built in the 2000s, operated through the 2010s. In parallel with operating in the 2010s, we then built the upgrade of it, which is now coming online these years, a bit disrupted by COVID, you know, as everything, and is now meant to operate through the 2020s into the 2030s, when we hope there will be another upgrade, and this will keep operating until the 2040s. So that's, you know, the time scale here is, if you want to follow the story from start to finish, the time scale is a human working life and longer. So that's important, because if you want to talk about, you know, the sociology and the incentives and what makes experimental physicists tick, and the stuff you mentioned about prizes and recognition and so on, the timescales really matter, right? Because
yeah, absolutely.
for
And we will get there, because it's for super
human
interesting.
beings, this stuff really matters.
Yeah.
It's just a fact. So that's one thing. Now then, in terms of how we do this, okay, the detector has many parts which are designed to do different things. So we have one piece of detector which surrounds the region where the protons are colliding at the Large Hadron Collider, and measures very precisely where those collisions are happening, and measures the initial trajectories of everything coming out of those collisions, okay? Of the charged particles coming out of those collisions. And then those charged particles go through a magnetic field, which deviates their trajectories. Then we have additional detectors after the magnetic field, which pick up the trajectories again. And from the curvature, you can infer the momentum of the particles. Then we have other detectors placed at various points along this route and after it, which help to identify the type of particle you're looking at. So is it a pion, a kaon, a proton, an electron, a muon, and so on. And all this data comes together. And right now, if we look at this upgrade version detector, this thing is recording up to 30 million crossings of the LHC proton beams per second.
Yeah, so maybe let's start. Let's start there because I know this stuff.
Yeah.
But, so it's an amazing instrument, the LHC.
Right.
So let's start maybe with the ring.
Right.
So what is happening there and why?
So what's happening is that the protons are getting. So first of all, the protons.
So we accelerate protons in the ring.
Exactly,
right?
They get accelerated, and at the same time they're getting accelerated and they're getting focused, because to collide, to make the protons collide, you have to really have a super.
So it's like packets of like this size, right?
Right. So
and
you
they go. They collide. The packets collide, and inside the packets, some protons collide head on. And when they collide with this big energy, they explode, right?
It's actually, for technical reasons, it's at a slight angle. It's not exactly head on, but yes, it's happened. But as it happens, exactly. And so the idea is the following. The idea is that when you collide protons, then you can create new matter and antimatter out of the energy that they're carrying. And the more energy you put into the protons, the heavier the objects you can create.
It's the famous C equal to mc squared, right?
Right. And so the first thing is, of course, you want to see if you create any new particles which are beyond the standard model. So that's how the Higgs was found. Well, the Higgs is part of the standard model.
Yes, so that was the last particle that we had to experimentally detect, right?
Yeah. Exactly. And then you want to see if we find any others. For the moment, no. But then you also can create an enormous amount of particles which you know exist, and which are going to then decay within your detector. And by measuring their decay products, you can actually make very precise inference of the properties of those particles. You can maybe be interested in how they are produced, but you can also be interested in how long do they live on average before they decay. You can be interested in measuring their mass very precisely, or in our case, measuring the difference between the behavior of the particles and antiparticles. And the very exciting thing about this is that particles are quantum mechanical objects. So when you talk about the internal structure of a particle, it's not like, if you have the internal structure of your phone, okay, your phone has some components. And if you took it apart, you could enumerate the components, but there's a fixed number of them. They're there. Well, that's not, with a particle, if you take a particle which you say consists of a quark and an antiquark, but that's not really true, because all around that quark and antiquark, you have quantum mechanically other quark-antiquark pairs coming out of the vacuum and going back into the vacuum the whole time. This is also true with the protons that are colliding, by the way. The protons, there's also, inside the proton, you have the gluons, whose strong force is actually holding the quarks inside the proton. Okay, and then you have other also quark-antiquark pairs popping out all the time. And when the two protons collide, it's any of these things.
Yeah, it's like a soup of energy, exactly. Right? Like you have carrots in it, you have some pasta, you have some meat, and then they are glued together, and then when they collide, you have this huge mass coming out of it.
Right. But this also means that you can have, if you believe that you have new particles, then in these interactions, you can also have these new particles, which appear very briefly, virtually appear, participate in the interaction and disappear. And because of how quantum mechanics works, even if those particles are too heavy to be produced directly in your proton collisions, they can still play a part. They can change the behavior of the interactions, let's say by having this quantum effect where they participate in the interaction without really being created.
Okay, so basically I'm getting very excited, but
and so you can
let's go back a little bit because this took me a while to understand, so it's maybe easier for the audience too.
Yeah.
So basically you have to have enough energy in the collision,
right,
corresponding to the mass of the particle you want to create, at least.
If you want it directly created,
Yes. So it's the energy that creates a particle that has a mass. So in the energy, you have to have enough energy. Right. And so when you say known particles, those are the particles that we have in the theory, the standard model, and we already experimentally detected and measured the properties. And that theory seems to be complete. The theory doesn't point to anything new. There are some things that we don't understand. And one of the hypotheses is that there are some other particles that are not in the standard model. And so now the experiment, now that the Higgs is found, so the standard model is complete, the goal is to just look and see if there are some other particles that show up. And what you're explaining is that those particles are probably very massy. Like they have a huge mass, bigger than the energy that we give in the collision. But so we will not find those particles, but we may find it through looking at their effect on what happens in the collision, right?
Right. So just to say, I mean, the standard model is complete once the Higgs is found. This is correct. I think what the way I would probably phrase it is that the standard model is a complete and internally consistent theory of the microscopic world, but it cannot explain, it's not, there are things in the macroscopic universe which cannot be explained through the microscopic constituents in the standard model. So,
and you're not talking about consciousness, right?
Well, we can get there. No, but I mean one.
But like the dark matter.
No, but exactly right. No, I mean there are various things, right? And then because if you for example, let's take dark matter very briefly, which often gets mentioned. Dark matter is a statement about the mismatch in various cosmological observations with which are just not consistent. Combining gravity with the postulate that the whole of the universe is made out of visible, i.e. standard model matter.
Basically the galaxies are not moving the way they are supposed to move, right?
Exactly. That's one, right, exactly. There are various symptoms, but the real point is the mismatch. It is that you say, okay, if the whole of the macroscopic universe is made out of the microscopic constituents in the standard model, then, and all of matter is essentially visible, then there has to be an alignment between these sets of observations of how the galaxies move and the predictions of general relativity and so on, and they just don't align. And therefore, there is this postulate that there is this stuff called dark matter, which are particles that are not in the standard model, and they're dark because they don't interact with light. And so that's how you, so that's just one example, but there are all kinds of motivated reasons why people are not very happy with the standard model as the kind of final theory of nature. But then the question becomes, at what energy do additional particles or additional forces manifest themselves? And this energy does not have to be anything accessible on Earth. Obviously, as
It's
experiment.
already what we do in the LHC is already something supernatural in the sense that it doesn't really happen on the Earth, right? Maybe with cosmic rays, you have this kind of energy, but those are very hard to
Right,
observe.
right,
Yeah.
right. And you can even be beyond that. And the thing is that as an experimental physicist, obviously you would like this stuff to be accessible, clearly. Accessible in the sense you can smash protons hard enough and then eventually they'll pop out. But maybe it isn't. And if it isn't, then this indirect approach, where you look for these subtle quantum mechanical effects that these particles can have on the behavior of those particles which you are able to observe in your lab directly. Maybe that's your window into understanding what is beyond the standard model. These things are complementary. It's not either or. It's you want to do both. But my experiment was very much built and designed for this indirect path. So make very, very, very precise measurements of certain types of particles that we know already exist. And then confront those measurements with standard model predictions, try to understand where do I deviate and what is this telling me.
I see. Okay, so this is what the LHCb experiment is built for, right?
Right.
So basically you have this big ring, it's like 27-kilometer diameter,
Right.
circumference.
27, yeah. 27.
It's partly in Switzerland, partly in France. That's the LHC, the Large Hadron Collider, where hadron is because it's protons.
Right.
And there are 4 detectors on it, right? The
Right.
Atlas, CMS, Alice,
Yes.
and the LHCb. And the 2 big ones, CMS and Atlas, were built to detect and measure the Higgs.
Right. And they were, and at the time, we were all hoping that there would be a whole soup of new
Yes.
beyond model particles that would pop out together with the Higgs.
And there's just silence on the histogram where these new
Sadly,
particles
that has
should
not
pop up,
been the
right?
case. Yeah. Sadly, that has not been the case, unfortunately.
Yeah, so we'll talk about that because that raises a big question of where experimental physics and physics in general is going. But so let's go back to the LHCb. So you are part of the collaboration, right? So this is a big collaboration. How many people?
Depends how you count, but somewhere between 1 and 1,500. Depends if you count members, authors. We're now big enough that we have so many categories of being associated to LHCb that I honestly can't keep track of it.
Okay, so it's like it's like an order of magnitude bigger than the Dunbar number then. Because I was in an experimental physics experiment which was roughly a village, and it felt like one. But this is bigger, so it has to be hierarchically organized at that point, right?
So LHCb, so yeah, it's interesting actually. We were small enough to begin with that we were not very hierarchical. And we've actually tried really, really hard to maintain as much of the non-hierarchical culture as we could. Now, of course, yes, you cannot manage 1,500 people the same way you manage 150 people. I mean, you can try, but you're going to fail.
Yes.
But it's complicated because there are many things that you can do a lot more efficiently when there's fewer of you. That's obvious. And also, right, this is not the private sector. So you cannot simply go and hire overqualified people by throwing money at the problem. You have to train from scratch and accept that the majority of people you train will have to leave the field whether they or you like it or not because of the
because these are mostly PhD students, right?
Right, and some stay as postdocs, but the pipeline is very, very narrow. And so you have a huge turnover in terms of having, let's say, a huge effort has to go into training people, et cetera, et cetera. It's actually one of the things we invested a lot on in the last years is trying to make it much more efficient in terms of people's time to train newcomers, because this became an obvious point where it just wasn't working for anybody.
Okay, so just to make sure that you understand, the problem is that the PhD students, right? They come in after graduating from university and stay 3, 4, 5 years, depending which country, right?
Right.
And then there is just not enough job in physics to keep these people in physics, right? So they basically go into physics because we'll talk about it, like, for example, why you chose this field. But then it's, for them, it's a temporary adventure, basically. And then they go out and they go into tech, they go into finance, they go into private industry. Some of them show up in AI, and we know them.
Yes.
And but so AI is a little bit different because the pipeline was like that before. I think in all academia, I don't know the numbers, but maybe it's between 20 and 50% of the PhDs that can even get a postdoc. The rest goes into industry. But in physics, it's probably even worse, right? Because the only job is that what you do. To
So
become
getting the first postdoc, if you're really determined to get the first postdoc, your chances are not so awful, because the amount of time that people invested in training you during your PhD, it's absolutely in the field's interest that you do a postdoc. The question is actually that there's this, well, there are many questions, but one of them is that there's a severe misalignment between the skills that are useful on a day-to-day basis for keeping the experiment going and the skills that are useful to universities when they look for who they want to give a tenured academic position. That is not the same skill set.
Okay, so tell me a little bit about this. So what are the skills that, because it's really hard to imagine how, even for a scientist, how something with so many people working on the same thing, collaborating, works. Usually even like large biology experiments, it's maybe 50, a lab of 50 people, but that's like a big size. In computer science, we have even smaller teams. So how is it organized? What are the basic things? What is your daily job as a PhD student who comes in and does something for LHCb? What are you training them for?
Okay, so if you're a PhD student, typically, obviously there are exceptions, many, but typically what happens is you will work on a physics analysis.
Which is what?
Right. And let me get to that in a second.
Okay, sorry.
On one part will be a physics analysis. And then the other part will be, you will do something, typically it's called service work, but you will do some technical job for the collaboration. Okay. So the physics analysis is actually the easier one, I think, to understand. We publish, roughly speaking, between 50 and 60 papers per year, what we call physics papers, because we also have technical papers, but they're a separate story. A physics paper, physics analysis, means you're measuring some fundamental property of nature. It can be, say, a mass of a particle, a lifetime of a particle, how often the particle is produced, how often the particle decays to certain other particles, some matter-antimatter symmetry. You search for some new particle that nobody's seen before, all that kind of stuff. But you're making some statement about some fundamental property of nature. Okay, and each analysis, what the analysis part is very much compartmentalized. We have, I think, at the last count, 9 different working groups that everybody's subdivided into, and each working group is responsible for a certain type of physics analysis. It's a combination of the technical elements that go into doing the analysis come together with the specific area of physics it's probing. Within each working group, so you will have 50 to 100 people, depending on the specific.
So each working group is a little hierarchy, has a head.
Sure, you have some
subgroups, and the subgroups at the end you have smaller groups of like more classical scientific teams that work on something very specific.
Right, and each physics analysis, a typical physics analysis, somewhere between 5 to 10 people. I haven't looked at these statistics, so I mean 5 to 10 is a kind of guesstimate. You have some which are bigger, and you have some which is like a supervisor and their student, and that's it. But typically you're 5-ish, maybe 10-ish. And so that part, actually, as you scale up the size, doesn't factorize so badly. because mostly, most of our data, well, all of our data undergoes a lot of central processing until it's kind of small enough, and we have a lot of centrally produced simulation detector as well. And a typical physics analysis will take the data, take the simulation, essentially confront one with the other, and use a combination of the it uses the simulation to make inferences from the data, to put in the most general possible terms. Well, it's all broken down to the point where a group of 5 people can do it effectively. And typically you can reduce the data enough that you can transfer it, maybe not to your laptop, it depends, but to your university cluster. And then, as you say, so that kind of factorizes out. You have the working group meetings, you exchange, you present on a semi-regular basis, you discuss, you ask each other questions, you try to learn something from what the other people in your working group are doing. You spend a lot of time agonizing about bugs in the data, which are, going to affect the analyses in your working group in common, and how you assign, how you fix them, or how you assign uncertainties to do with them. Now, technical work is very different, because the technical work, the orchestra has to play together.
It makes sure that the data will arrive, right?
Right. And here it is factorized, of course. Each piece of the detector is organized in something called a project. The software is also, since a few years, organized in projects. So you have one project for the simulation, one project for the real-time aspects, one project for the what we call offline, the aspects that happen once the data is already in permanent storage, and one project which deals with the core infrastructure, the kind of framework and shared components that glue everything together. And you have this, as I say, the different pieces of detector and so on. But they're interdependent. Mm-hmm. So quite frequently, if you have an issue somewhere in your detector, you might see it, the people who are working on that piece of the detector might see it at a very low level in when they're monitoring the electronics, for example. But then you might also see it in your higher up inside the software when you're doing your central processing of data. And then you have to kind of correlate the two and understand how important it is, how much a data sample is affected. Is this really going to bias things?
So it goes on Slack and then propagates to other projects.
Yeah. So there you cannot afford to just compartmentalize, but it's complicated because because you say it's a very large number of people, but with a how to phrase this, nobody, not even the people in charge of the collaboration, nominally in charge, because we sort of have a management team who are nominally in charge of everything, but nobody has any of the usual levers that you would use to incentivize certain types of working practice available to them. Nobody's in charge of hiring for the collaboration. That just doesn't exist, right? I mean, the individual, we have what, 70 odd institutes in the collaboration?
How many?
70.
So and institute means like university departments or groups in universities and some research.
Exactly. And each of them essentially has its own incentives.
And it's like 20 countries.
Yeah, and sometimes their own incentives are imposed on them by the university which they're part of. Mm. You try to, at a national level, you have some degree of coordination, but it's sometimes. But the whole thing is very, very complicated. And you find yourself very regularly in situations, especially for technical work, where you need people with very specific skill sets. You need somebody who really knows how to program an FPGA. Okay. You need somebody who really knows how to program a GPU. You need somebody who really knows how to deal with the cooling system of an experiment. And you look around and you can't find a single university where the administration actually wants to give this person job stability. And
I see. Okay, so this is how it's related. Okay. So you hire these students, you train them for this very specific skills, and then they leave.
And so, unsurprisingly, no matter how critical, and that's the part which I think sometimes, if you were coming from the private sector, you would look at this and you would ask yourself, well, how does any of this ever work at all? is
Yeah,
that no
that's what I
matter
was
how
asking
critical this
myself.
person is,
Yeah.
there's 10 other people who are equally critical. So that part is very messy, and it's also messy because traditionally the technical work gets recognized through the quality of the physics work. And traditionally, it's very, very difficult to give a direct insight into the actual quality of the technical work standalone, right? But by being a subsidiary of what comes out of the physics, for people, I think one thing that the field, if you want my opinion on it, constantly overlooks is that people need to feel internally. It's not just about getting a pat on the back. They need to feel within themselves that what they're doing is meaningful and that they are invested in it and that they enjoy it, right? And these are a package deal. All of this stuff, you can't make a spreadsheet out of. If you give somebody this many CV points, then they are going to be happy. That's just not how human beings work. And if you're doing technical work and your technical work is constantly in the background, right, compared to that's if it doesn't have its own raison d'etre, but its raison d'etre is delegated to something you don't work on. So at that level also, it's not healthy that you factorize things.
So everybody basically wants to work on the physics analysis because for
not
those
everybody wants to, right? If you take an FPGA, that's actually an interesting point. If you take somebody who's super good at programming an FPGA, they might, in a private sector company, be able to get fully get their personal satisfaction out of just being really, really good at that, and feeling that everybody around, that not only that the individuals they work with, but that the system as a whole appreciates the importance of having them being good at that. In physics, it's much harder because system as a whole projects that what it really cares about is the physics results. Whether intentionally or not is another discussion.
because
because
in like a private industry, the FPGA expertise and what's coming out of it may be the end product that the company produces, right? And here it's hierarchies of dependencies, which at the end produce maybe a number.
Right. And exactly. So here you can have people who are not maybe even so fascinated by the physics analysis itself, but are super fascinated by building the most precise piece of the detector. It doesn't have to just be, it can be a silicon sensor, can be many different, we have many different types of technology, right? And they can be super motivated. This is going to be the best it can be. But the field finds it very, very hard, not just to give them job stability in some crude sense, but finds it very hard to communicate to them in a way that they are then able to, in their daily life, really, that it means something to them, that actually we need you, you're important here, and you're in a place where your skills are appreciated.
But somehow it still works, right? It didn't fall apart.
Yeah. It does. It does. And
it accumulates social debt somehow. How does it?
I mean, there's definitely, okay, so I think, we should put several disclaimers around this, right? So I am 41. So
and you get a permanent position. So you are one of the lucky ones who went up in the pyramid. And
But I've had a lucky life through the whole thing, right? I mean, I was born in Yugoslavia. I was lucky that my parents chose to pack their bags and get out. Well, chose, and also had a friend outside who was able to get them out when
that was in the 90s during the war,
right?
Right.
I got a foreign education. Well, most of the kids I grew up with got what they got. And then I got a chance to study in the UK to a very large extent, because in the 1990s, the government there didn't have the same obsession with immigration that they do now. I mean, I often say to people that, what back then, my mother was able to come with me while I was there in high school, and so on. This would just not be possible to them. That arrangement would just never have worked. Went there, got an education, got a university education, got a PhD eventually. Was also very lucky that my parents were very supportive of all that. And then but the real luck was that I got to be around for the start of the LHC not through any particular brilliant choices of my own, but that's just how it worked out. I ended up being at CERN in 2009 when everything was sort of kicking off.
So how did this happen? I'm wondering, because one of the questions that I
I
ask
don't know how it
everybody is
happened, actually.
like how did you choose physics? Your father is an economist who was actually a minister in one of the post-Yugoslavian governments, right?
My father isn't he was never actually a minister. He
Ah.
he wasn't, but he was an economist. And my mom was by training a logician. She did formal logic.
Oh.
When I was a kid, I knew it was going to be physics or computer science.
So why?
I can't tell you why. That's the funny thing. I can't tell you, but I knew. If you go back, I thought about it because you kind of warned me what you wanted to talk about. So I really thought about it. But for as long as I can remember being myself, I knew that I wanted to do fundamental science of some kind. And I liked computers, but they didn't feel fundamental enough. So physics was like the thing in that sense. But as to why, I couldn't. I'm not sure. I know why. It was just always there.
So for me, maybe this is a bit provocative, but let's say for me, physics, either if you go to astrophysics where you study things that are very, very far away, or you go to fundamental physics where you study things that are tiny. That's sort of like the furthest away you can get from this world where you live in, right?
Yeah, I mean, so what is certainly true is that there are many practical aspects of life where I think most people who know me would tell you that, I'm not the guy that you give a drill and ask him to hang you a painting. I'm not the best person in the world to ask to organize a social event or what have you. I mean, what can I
Those
say?
are very different skills, by the way, no?
No, I know, but what I'm trying to say is that, like, if you talk about getting away from stuff, it's true that I'm often happiest in my own head. That's true. But I'm not sure I don't know actually, but I'm not sure if that's to do with physics. But I kind of I guess the curiosity was definitely always there and was always encouraged. I was encouraged to be curious. Um, and then why fundamental physics as such, why particle physics as such, that actually genuinely was to a large extent an accident, which is kind of well, I mean, without mincing words, I made an almighty mess of my undergraduate education for all kinds of reasons, personal.
What does it mean?
Well, I mean, there were some of the exams that I very nearly failed. At least one of the exams I turned up to it not even knowing what was on the syllabus, and how I passed that one, I genuinely don't know. And so at the end, actually, my thesis advisor was one of the few people who remained patient with me after that entire episode. So that's in many ways how I ended up on LHCb. He didn't have infinite patience. Actually, at some point, about 2 years into my PhD, when I was still not producing any results, he sort of told me that I needed to decide if I actually wanted to do something with myself or not, and that was actually a kick in the derriere that I desperately needed. But that's fine, But even then, like, as I say, the thing about being somewhere at the start, I wasn't there when LHCb as an experiment was conceived, and I wasn't there when it was really being constructed. I was a student. I was a student doing simulation studies. I didn't touch the detector ever. but I was there when it was turning on. And I was there when data started flowing through it. And then I had the internal motivation to go and say, okay, well, let's try and make it do something if you want. And let's really contribute to the technical aspects of how we take the data. And for me, I got attracted to the real-time aspects.
Okay, so maybe let's explain that. I wanted
Yeah,
to ask.
yeah. So this is what was the protons. The proton beams can cross up to 30 million times a second.
30 million.
30 million, right? And each of those crossings can produce, in theory, multiple proton-proton collisions. As it happens, the way we ran the experiment the last 10 years, we typically tuned to produce between 1 and 2.
Because you
Now,
can tune it because you can focus the beams, right? So
right,
how many
right.
protons? That's something you can tune. Huh?
Well, we actually you could focus them. We actually separate them spatially so that they don't have their full volumes, if you want, coming into contact with each other. But you separate them out. It's only part of, if you think about two cylinders, so we make them go like that. But anyway, the result is the same. But still, this is a lot of collisions, and each of these collisions is producing dozens of other particles that appear in your detector. And when you compute the volume of the data that we're discussing, in the previous 10 years, this was, what are we talking about? This was a few terabits per second. And now in this new period, it's like 30 terabits per second, roughly 32 or something. It depends a little bit. Right? So clearly, that much data, you can't just dump it all to hard disks, right? You just can't. And even if you could, you couldn't send it around to all the physicists. So you have to reduce this thing by like 4 orders of magnitude.
Before you ever save it, right?
Right, and you have to do this in real time. And the reason I got excited about this was because it was obvious to me that this was the part where we had the maximum difference between like what a good implementation and a not so good implementation, the impact it would have on the ultimate sensitivity to the physics.
I see.
Because
and just a little bit of detail. So basically, this is the part of the whole detector and software pipeline where you decide what to keep and what not to keep.
Exactly.
So if you fail here, the particle that you're looking for might be never found because you just threw it away before even saving it. So you have to make it very sure that all the interesting events are saved, right?
Exactly. And that looked very exciting to me and very interesting. And that team was tiny. When we started taking data, this was like really a few people. We literally fit into the physical office of the person in charge. We used to kind of gather around and we'd have a Skype conversation with some colleagues who were in Brazil. So we'd have a Skype conversation with them. That was how we organized.
When we used to use Skype.
Which, of course, if you've just finished your PhD, you're doing like you're a postdoc. It's actually very nice to be in an environment where there's not so many people because you feel like you can find a place for yourself in that.
And those incentives come from the people you work with. Those that you are missing for the technical work that you were talking about, no? So when you are in a smaller group, you can incentivize each other.
Yeah, right? Although, I mean, I have to admit, at the time, I never gave any thought whatsoever, and I know this probably sounds hard to believe, but I never gave any thought whatsoever to my career at all. After my PhD, I spoke to my advisor once, saying, well, what do I do next? And he sort of suggested, well, there's this postdoc that's been opened. Why don't you apply for it? And then during that first postdoc, which was in Glasgow, I was out at CERN because I wanted to be out at CERN. So I went out to CERN and I ended up having a chat with another colleague and said, oh, why don't you apply for this fellowship at CERN? I had to actually be sent to my first conference. I didn't think to ask anybody to go to a conference. I ended up, one of the older people in the experiencer came to me and said, oh, we're going to send you to this conference. So to me, so I was very, but because I was there as this thing was ramping up, you know, I was kind of in an upswing of things where that was okay. Today, the PhD students, because now we're, you know, now we're well into the swing of things.
It's almost like a Ponzi scheme.
I would never allow my PhD student today, or I say allow, but I would feel as a supervisor, I feel compelled to explain to them, listen, like you have to try to get conference talks. You have to do, you have to plan your career, like have a plan, do everything I didn't do, you know.
And the PhD students usually who come in, they have the dream to stay in physics, right? They all want to stay in physics as a plan A, right?
I don't know about all, because there's so many. There is definitely a fraction who finished their PhD and already at the end of the PhD realized that long term this is not for them. But there's quite a few who really want to keep doing it, and then it's just not possible. And that's the part that's a bit rough. Well, it's more than a bit rough for them. It's quite rough. But so then, you know, at that start, it was also one of those kind of dream situations where everything is so rough that any improvements you make sort of automatically look really good, because you're building on a, you know, fairly low baseline. And that, of course, was it meant that I was able to learn a lot while making mistakes, which is always precious when you have the opportunity to do that. So I feel very, you know, I say very lucky about
okay, so you started to work on this real-time component of the software, right? And if I remember correctly, when we met, you were on this, and you were one of the first proponents of using AI and GPUs for this, right?
So yeah, so okay. Think about, let's do AI first, because GPUs are a bit separate. I went through various phases with GPUs. I was kind of excited. Then I went through several years where I convinced myself this would never work. And then we ended up making it work, but we can get to that in a second. But the AI part is actually funny because nowadays.
So how does it work roughly? Yeah, even in the analysis and in the trigger is the real-time part. Separates from what you keep and what you don't. So where do you use AI there, and how do you use it?
Right. So let's take a step back. And you know, when people say AI nowadays, you probably think, you know, ChatGPT. You think, because that's what everything's been about the last couple of years. You think these massive neural network models. But from very early on, really I would say from 2010 already, and certainly from 2011. It was very clear that that we needed to do what I would call more prosaically multivariate analysis. Okay, so the point is, what problem are you trying to solve? And the most typical problem we try to solve is a classification problem. We have some signature, and we want to know, is it our signal or is it some background mimicking our signal?
So let's slow down. So by signature, so signal means the interesting event, and background means the ones that's just noise, that's something that's known, and signature means that your million electronic channels that give you some data. In that space, you can separate the interesting ones from the non-interesting ones. So it's a classical classification problem.
It's a classical classification problem, and what you do is you have something called a reconstruction, which builds you a bunch of features basically from your million electronic channels. And really what it is doing is it finds the trajectories of the charged particles through your detector. It finds the places where the neutral particles impact your detector. We have a piece of the detector which is dedicated to basically, it's like a wall. We call it the calorimeter, and the neutral particles just impact it.
Neutral means like neutron.
Or photon, you know, neutral pion.
Okay, because they don't curve in the magnetic field, so they are harder to detect, right?
Right. So those are the two basic things. You have trajectories of charged particles, and you have the neutrals, and this gives you a bunch of features. The trajectories, of course, have geometric features. Where did they originate from? At what angle, and so on. And they have what we call kinematic features, which is basically the momentum of it. And you have what I mentioned before. You have detectors dedicated to identifying the type of particle. So you have what we call particle identification information. But the point is, it's a finite set of features. And so, of course, the vast majority, and this is still true today, the absolute vast majority of what we do is done with boosted decision trees. Because the fact is that for the vast majority of classification problems, it's good enough. And you don't, the gain that you might get from going beyond good enough for the classification aspects is just, the juice isn't worth the squeeze.
So for those who know AI, where do you get the training data from? So because in the detector you just see the signature, you just see the features. You don't know what's there, right?
So the train data for your interesting, for what we call signals, your train data is simulation typically. There are corner cases where you can get this out data as well, but typically you just have simulation. So we have very sophisticated simulation of the passage of particles through the detector, of the collisions and so on. And this tells you your signal. And then for background, it depends. Sometimes you also simulate the background if you have very specific processes that are going to, mimic or fake your signal. And sometimes for the real-time aspects, typically you just train against random collisions in data, randomly sampled collisions. Because, if you're going to keep 1 in 10,000 collisions, that means that if you train on 10,000 randomly sampled collisions, your contamination from stuff you care about is basically zero anyway. So why do you care?
So, but then you said that the most interesting stuff now here is to find new particles.
Right.
New particles that you cannot simulate because you don't know them. So
right.
what do you do for them? How do you make sure that any interesting new particle is saved when your classifier is trained on known stuff?
Right. So now that depends where you are, right? So Atlas and CMS, you mentioned, they care a lot about this, and they put a lot of work into anomaly detection, and different ways of trying to even extract this just from data without simulation and so on. For us, we have, for the most part, we followed a much more prosaic path that you simulate well-motivated beyond standard model scenarios. And you assume that anything else is, if you're efficient on them, then anything else will be close enough. But the thing is, right? So we really went deep into decision trees 2010, 2011. So before, before the AI, the AI summer, or I'm not sure what people are calling it now. Certainly it's not the winter anymore, right? So is it the spring or the summer? I don't know. But before that happened, and then when the neural network rebirth happened, we spent quite some time actually looking into, okay, are there places where neural networks objectively give a lot of extra performance, and also deep versus shallow neural networks. And there are some areas where we use neural networks, in particular on particle identification, because there are some places where it's not a pure classification problem, or posed in another way, where you need the network to effectively build the correct feature for you, right? Where you want to let it basically rotate the feature space around to improve your separation. Because if
it's a little bit like computer vision, no? Right?
Well,
you really go from pixels to decisions. Yeah?
Yeah, I mean, in some sense, it's all topologies, right? A decision tree fundamentally is just some n-dimensional binning in your feature space. And that's actually the attractive part of it, that you can intuitively, especially if the number of features is reasonably small, you can still sort of intuitively understand what it's doing. And a neural network is a transformation of the raw inputs, which can then build you a completely differently, the number of dimensions and which dimensions it can build you. So it can enhance the topological separation compared to the features you might have. But it turns out the number of cases where that's really important for us until now is actually not that big. Interestingly, where I suspect where this has actually gotten the most traction is exactly on the simulation side. Because there are things, and in particular around simulating a calorimeter, for example.
It measures the energy of the particle.
Yeah, because when the particle
Mhm.
comes in, it doesn't just, how does it deposit the energy? It deposits the energy by having interaction with the material, emitting other particles. It essentially radiates the energy little by little. And this is a process which fundamentally is very, really hard to fully simulate anyway.
I see.
Very time consuming to simulate, certainly. And if you want to learn it, it's not a classification problem, it's a regression problem. And to learn it there, a neural network is genuinely better. It just fits the problem better. So it's not like I'm not saying that it's pointless, but it's just to say that I just wanted to like really make clear for people that, because you will read a lot about how particle physicists use AI, and it's true, and there are places, but as usual, you respect the principle that the simplest tool which gets the job done is the tool you want to use, right?
Yeah. No, but I don't think particle physics is alone on this. If you ask people in tabular data, they are still using XGBoost and stuff. But there was one more interesting feature when
We
I
all love
worked on.
XGBoost. Mad respect.
So there was one more interesting aspect which I learned in physics, which is that you train on simulated data and then you test on real data, and those are not the same. The distributions are different. You have shifts, you have things that you don't understand, you have things you understand. And then, so you have to deal with what you call the systematic errors,
Right.
which are not statistical by nature, because AI is based on the intuition that if you have a big enough neural net and big enough data, then you at the end you learn the ground truth because of some statistical properties. As you increase the number of data, you're more and more approximating the distributions where the data come from. But in physics, this is not completely true, right?
No, that's correct, and that actually I think connects in a very interesting way. But you can tell me if you think this is sidetrack. But I think it connects very interesting way to this points that I saw you making on social media about propositional knowledge and so on, because this is an absolutely classic problem. Systematic effects are an absolutely classical problem where the real question you're asking yourself is, what should I prioritize caring about? Because in principle, you have an infinite amount of unknowns about your detector and its behavior and your signals and your backgrounds and so on. And depending on the physics analysis you are doing, you certainly do not have the time to investigate them all in detail for this analysis today. Over a long enough period of time, you hope that the collaboration will investigate, all of them to some level. But you have to make a judgment that is on what you're actually going to sink the finite amount of time of people that you have. So you have to make a lot of very, approximate first principles arguments about, okay, this is likely to be a big effect, this not so much. And of course, the one thing we haven't talked about is the collaboration is so big that we have all of our publications get scrutinized internally long before they go to a journal. So you have, typically you'll get scrutinized inside your working group, then you leave the working group, you have independent reviewers typically from outside the working group appointed, then you have another layer of scrutiny. Then after the paper circulates to all collaboration, you have yet another layer of scrutiny. And all along the way, you have people who have their own priorities and their own opinions about what isn't important, who might bring it up. And so you explore these different effects. But really, the tools you have are not so many. So typically, if you want to explore a systematic effect, your dream scenario is that you have a similar measurement where you know what the answer should be because somebody else already did it. And you can carry out that measurement. You can sort of see, okay, am I compatible? So then
you check your simulations against those.
Yeah. And then your method is great. You can have internal closure tests on the simulation. So you can simulate, you can inject into the simulation, for example, detector misalignments in the detector, miscalibrations. You can inject the physics you care about. You can take, you know, simulation and inject matter antimatter symmetry and see if you can get back the value that you injected. So there are these kind of ways as well. But a lot of it comes down to the say, and in a lot of reviews, what it really comes down to is, okay, what do we actually have the time to go through before we say, okay, well, this is good enough.
Okay, because usually as I remember, the kind of decisions you have to make is that, okay, I see something there.
Yeah.
Compared to simulation, let's say a new particle.
Yeah.
Is it, first of all, is it just a statistical fluctuation? But statistical fluctuation goes away with data. So you can just wait more, you collect more data, and that fluctuation goes away. But if there's a systematic effect, it means that your simulation and reality has a mismatch that looks like something interesting, something new. So what you want to avoid in this analysis is to misclassify a hardware fluke or something unknown in the detector to something interesting physics, right? So this is basically systematic. And then you have an infinite number of things you could look at,
right,
where you find something interesting, and you just decide after a finite number of checks that this is not a fluke, this is something real.
Right. And checks, as I say, checks which are not what you're relying on, and actually one of the big strengths and why I think actually the system does end up working just to a very large extent is because you have, in the aggregate, you have an enormous amount of expertise and insight within the collaborations. And what you're really relying on is that the aggregated knowledge will mean that even though each individual reviewer and proponent of each analysis and person working on a detector and so on has their own private conception of what is and is not important to spend time on, that in the aggregate you will get you will converge towards the right balance, and actually that to a very large extent does work.
It is super interesting. So basically, because I remember, so you have a very high bar for publishing anything new in terms of statistical fluctuation. It has to be like one chance in, I don't know, 10 to the 7 to attribute the finding to statistical fluctuation. So, but what was really interesting to me is that this number also contains some quantitative statements about the systematics. So somehow there are two ways of discovering something in a false way, like something that's not there. One is a statistical and another one is systematic. And you find ways to actually with math and with some calculations to mix those two and give a number, put a number on what is the probability that what I found is not there. And until this number is not low enough, you don't publish, right? This is somehow the process.
So I think it's fair to say, I'm trying to think of the exact number. There's basically two things you're trying to protect against. I think, now this number may be a bit off, but I think that if you take all the LHC collaborations put together, by now they have published, I think it must be somewhere in the region of 4,000, maybe even up to 5,000 papers between them. And those physics publications, I think, I'd say, I don't number by heart. And if you look at, and each of those might have multiple measurements in them. So you're really looking at having measured a couple of tens of thousands, probably, again, let's say order tens of thousands of fundamental things about nature. Well, automatically that means that at least some of your measurements should actually be, if you've gotten everything right, deviating from prediction by, one chance in 10,000, right? And whatever that chance actually is for that specific measurement. And so one of the reasons why the bar is so high is because you do so many things. So the bar to have and even within one measurement, you might be looking for a new particle, over like an enormous mass range. And you might try like hundreds of different hypotheses of what the mass should be. So that's the famous look elsewhere effect. But then the other point you're protecting against is unknown unknowns. So you have, and this is a bit of a delicate point, but you have a kind of historical knowledge as a field of things you thought were real that turned out not to be, or things which you thought disagreed with theory or predictions, but turned out to be because the prediction on the theory side was not quite accurate. Usually it's a combination, actually. Usually it's a combination of some experimental effects. And so you also want to set the bar a bit high because you're sort of baking in the fact that, you know, some of this stuff is not going to be the real deal. And of course, there's a reason why both Atlas and CMS were built, right? The field, I think entirely correctly, generally wants independent confirmation with a separate detector before it.
Yeah, so you
Before
build
it
two
says,
detectors
this is
completely
the real
separated.
deal.
Yeah, okay.
Well, and it's normal, and it's normal because, as I say, the fake things, when you have such a complex system, it's actually almost impossible to, well, nothing is fully impossible, but it's pretty much as close to impossible as possible, as you can imagine, for somebody to just invent a signal out of nothing, to fully fake something. That just doesn't happen. And it couldn't with that number of people. It couldn't. I don't want to tempt fate, but you know. But even beyond that, even simples, if you have a single source of bias, so imagine you trained your classifier in such a way that it creates a fake peak. During your review process, you're going to get asked to train your classifier in different types of simulation. You're going to get asked to train it with different assumptions. You're going to get asked this, that, and the other. Well, one of those checks is typically going to uncover that you biased yourself, right? It's actually very hard for it not to. So the real problems are not the simple ones. The simple ones we know how to get rid of. The real problem is typically when you have a genuine fluctuation in your data, and then you have an unlucky correlation between that and some bias you introduced somehow either into your reconstruction or your classification or what have you. And then with some, typically on top of that, you need to also have some failure in your process so that some unlucky combination of the internal physics priorities or prior beliefs of the proponents about what is and isn't important, combined with the prior beliefs of their reviewers about what is and isn't important, that means that this isn't fully interrogated. And then you get, and of course, then having an independent experiment with an independent group of people and so on and so forth, because the idea is that because the biases are such a complicated coincidence of events, it's very hard for the same coincidence of events to go and make the same thing somewhere else.
Yeah, I see.
I'm oversimplifying it, but
so what I hear here, there's this beautiful picture of the Popperian scientific method, and then there is the real stuff, which is the goal is still the same, to avoid self-deception, but the methods are soft in the sense that not necessarily formalized. It's more like the community's history and memory and a lot of things that went wrong that you learned from, which reside in the brain of the people who are in the collaboration. They somehow make it such that what comes out of the collaboration as publication is more or less guaranteed to be true, right?
Yeah, I mean, high energy physics, I think, is probably as close to the Popperian ideal as you can get, because we can run the collider again. We generate a new data set. It doesn't, from that point of view, it doesn't get much better. But yes, you try to use the collective, if you want, as a strength. And maybe a more provocative way of phrasing it is that you can take the point of view that you want to eradicate bias, you want to be super objective. But sometimes it's wiser to just accept that humans are biased inherently, in the sense that we have individual preferences which drive us to spend, put our energy into some things and not put them into other things. And try to say that if you have enough people, a diverse enough collaboration with a diverse enough set of preferences, then on the aggregate, actually, the collaboration as a whole is not biased, even if each of the individual members has things that they deeply care about. And this, by the way, I mean, I say it's provocative because it, very often nowadays, especially with very large scientific experiments, you can very easily fall into the trap where all the communication is so sanitized in terms of the language that's used that it's difficult to talk about stuff without sounding like you're, oh my God, you're accusing people of having a bias. Well, no, but everybody who's worked in a large collaboration knows that you're doing a certain kind of analysis, and a specific person, name, surname, is always going to ask you the same question. And we all know, we all know who's the colleague who's going to ask you question 1 or question 2 or question 3. And it's because they really deeply care about this thing and they want every single person to check it, whether it's really relevant or not. Well, clearly that's because they have a kind of, you could also phrase it, they have a bias towards this being important and towards something else not being important. And that's my point. That's okay. As long as you have enough people with enough different perspectives, that's a strength. That's not a weakness.
Yes, absolutely. So that's actually a strength of big collaborations.
Yeah.
You can cover more or less, I mean, not everything, but everybody's personal biases just add up and cancel each other out, right? So I'd like to ask you about how this, like the bigger picture of physics, like how this field works, because when you brought up propositional, I thought we were going in that direction. Who decides what to go after? Because this is not part of the scientific method.
That's a very good question. I would like to know the answer myself. I mean, I think all of us actually, especially nowadays when we're waiting to find out what's going to happen after the LHC, I think everybody who's a grunt like me, because I mean, the vast majority of us in the field are basically grunts. I think we'd all like to know who's going to make the final decision. But the fact is, there's no simple answer. It's a combination of having a critical mass of, well, let's not be cynical about it, because actually I think the reality here isn't that cynical. You have to have a genuine combination, critical mass of physicists who really think, okay, this is going to tell us something fundamental about nature. And then, obviously, the cost has to be to some extent right. The cost that typically gets talked about is the financial cost, but the human cost to me personally, is more important, but I think at least should be treated as equally important. LHCb, and we are the smallest of the 4 big LHC collaborations. We alone produce order of 100 PhD theses per year, roughly. Maybe a little bit less, but not much less. So, you want to run us for another 20 years, you very quickly see how much, that's a lot of PhD theses, right? And that's a huge amount of human knowledge, also the amount that you're investing in training people in a very, in a specific way, and so on and so forth. And you can then have arguments about whether this is a zero-sum game with respect to other fields or not, and there are different points of view, but that's a very important part of it. So that cost, financial cost, so comes into it, and the infrastructure aspects, of course, come into it. Once some governments want to have big labs in their territory, and some don't. Generally, a lot of governments do like big infrastructure, and once they've built big infrastructure, they tend to not like that much dismantling it. Well, unless then their political opponents get into power, and then you can, but my point is, it's complex. It's complex.
It's a messy political process. Yeah.
It can be a messy political process. Sometimes the thing to do is obvious. So when the Higgs was proposed, once you're convinced technologically you're able to probe towards it, this was the famous no-lose theorem. There had to be the Higgs, or there had to be some other new particles. But at the TeV scale, there had to be something visible. There just had to be. And there was, and it's the Higgs. Well, there isn't such a no-lose theorem at the moment in that sense.
So it means that basically the community is divergent because there's no obvious next thing to do. But at the same time, there's this convergence requirement because unless the critical mass is there, it's hard to ask the politicians to finance
right.
it.
And
right?
one of the people who follow you on Twitter asked about the linear collider, for example. And it's interesting because the linear collider in principle allows you to study the Higgs more precisely than the Large Hadron Collider, not as precisely as some of the other proposed lepton colliders or let's say future circular collider or the muon collider, what have you. And although it has some unique advantages, the linear collider, in terms of the polarization, but the real point is a linear collider fundamentally, from an infrastructure point of view, is not a road to somewhere. You build it, you do the physics with it, and then that's kind of it. You can upgrade its energy a bit to look for new particles at a bit higher energies, but it doesn't scale well beyond the initial investment. And of course, I mean, it's understandable, right? If you're proposing something that's going to take 10, 20 years to build, put in place, and then going to be operating for another 10, 20, 30 years. Mm-hmm. I mean, you want the complex that you're building to be, to have a path where it's going to be usable beyond that. For all kinds of sociological, political, ecological, whatever you phrase it, reasons. It's a completely, but of course that doesn't make things converge faster, and it doesn't make it easier for let's say people at the grunt level, like yours truly, to feel like they have any meaningful input to the process. Now, then it depends on your, let's say, I mean, I've had a very, very lucky life and a very, very lucky career. So I'm not sitting here crying about my fate because I don't get to personally decide what next collider is built. Let's be clear, right? That's fine. But it can lead but when given the size of the field, it can lead, if you think about now a PhD student coming in, and unlike me, they don't get to be there at the start of a new detector coming up. Okay, with the total like tabula rasa in terms of like there was no LHCb before, and actually for us what was also super cool is the expectations were very low. The last time anybody had tried to do our kind of experiment, a hadron collider, something called HERA-B, that most of the field prefers to forget because it was a very sad failure. So there were many people who just thought we would totally fall flat on our face. So basically anything was a win, which again, when you're starting out, when you're in your 20s and this is the that's golden. And it's very hard. The students they just don't have that. They have the weight of what we achieved in the last 10 years on their shoulders and trying to go beyond that. And they're in this now much more bureaucratized structure. And they look at the future, and the future is being decided, and it feels very far away from them. Well, and on top of that, the world around us has gazillions of interesting problems that you can spend your time and energy on, where you're closer to feel like you're closer to the problem, and you feel like payoff is somewhere within your lifetime.
Exactly. And that's exactly what I was thinking about. Like it brings back the very first thing you said, that right now in experimental physics. So let me just say this, like the Atlas detector was compared to a cathedral for its size, right?
Well,
yeah. But I think there is a more profound metaphor there, which is that cathedrals in the early 1100, 300, they were built by multiple generations. The people who started it didn't even dream about seeing the end product. So there is this aspect in physics now that Right now, it's basically if they're in the start of the process, maybe by retirement you see data, but it's getting into a situation where it's multiple generations. So the people who start the process will not even see the data. So it's new people who will come in and read and analyze it that will produce the results. So from this point of view, it became very much like building a multi-generational cathedral, right? And it's hard to imagine how it feels, because that comes back to what you just said, that in other fields like AI, it's like weeks, and in biology it's maybe years, but
Well, and I
it's
think
going much faster, right?
so. I think that that's true, but I think really there are three things, and any one of them, or even any two of them combined, would not really be an issue. But all three together make it very hard. The first one is the very long time scales. That really does make it hard. The second one is that if you do a PhD, and you really stick it out until the end, and you in not the end of the PhD, but you really say, okay, I want to be a particle physicist. You can be really good at your job, and you can be a really good physicist, and you can produce really high quality results, and you still have a non-negligible risk that the universities and the funding agencies will fundamentally say, well, we're very sorry, but you're just not what we're looking for. And that can happen. That typically will happen when you're in your mid-30s. That's a rough proposition. Those two together are quite rough on their own. And then on top of that, there isn't, and this one is kind of hard, but there isn't, I think, a kind of a simple payoff in terms of fundamental knowledge, where you can say to yourself, well, okay, I'm going to make this sacrifice and it's super risky, but at the end of it, if it works out, I will leave a real legacy of fundamental knowledge for humanity, really something new, not just, I measured this thing that we already knew about much more precisely. That gets into, and don't get me wrong, so I personally think that measuring stuff that we already know about much more precisely is an incredibly worthwhile thing to leave to future generations, because we don't have the tools to see the new particles today, and maybe we won't even have them 100 years from now, one day somebody will, betting against the collective. I'm fundamentally an optimist, betting against the collective power of humanity to make things happen is generally been a losing proposition for many centuries now, and I think remains a losing proposition. But when you have all those three things together, if you try to put it from the perspective of a 20-year-old, particularly a 20-year-old, if you think about a kid who's coming out of a family where they're not going to get an inheritance, and then they're being asked to do all of this on salaries where buying, having a stable situation of where to live looks like a total fantasy, and where most of the time the idea that they should be able to be able to live with their partner in the same country is considered a bit of a kind of luxury. Why are you worrying about that? Well, it's very easy to see why interesting problems in other domains that are able to pay, good salaries, have short time scales, yada yada yada. You can deeply be affected by fundamental physics as much as you want, but there are realities in life. And again, each individual case, you might be able to get out of, but once it starts being a problem in the aggregate, then you are in deep trouble, and that connects to specialization. And this is a real problem. Once the colorimeter is so big, you specialize, it's normal. At the same time, it means there are very, very few people who can still put the detector together from A to Z by themselves. Almost nobody, if we're being honest. Almost nobody. Well, that's a huge problem. We still have the generation that got to do Hall detectors by themselves because they were so much smaller around, but 20 years from now, we won't. And that's something that the field, I think, understands, and nobody has a very smart solution to. So yeah, it's a long-term problem.
So there are two more topics I want to do before we wrap up. One is what are your dreams for yourself? So we talked about, like, you know, this multi-generational idea of giving knowledge for the next generations in your lifetime. So what's the best scenario that you can imagine for yourself?
You know, that's a really difficult one. I mean, the most basic answer is that I somehow got to live the dream already, you know, and I know it sounds really, in a way, that sounds like a cop-out, but truth is, you know, if you look at what happened to most Yugoslav kids born in 1982, I mean, I've lived the dream in that sense. You know, I didn't get the war. I got the education minus most of the pain. Wasn't okay. Living as an immigrant in the 90s wasn't entirely devoid of xenophobic problems, but I think compared to most people, I had it pretty easy. And then, as I say, I got to be there for the startup of the LHC, and so you gotta, at some level, you gotta count your blessings. What comes next is a bonus. That's that's the reality. Now, of course, I'm not, you know, I have an appetite for the bonus to be, I'd like the bonus to be nice. I don't, I'm not trapped in some kind of total survivor guilt in that respect. And I would like very much to have a chance that there is the next generation of facilities, which is built on a time scale where I can make a meaningful contribution to its construction, and I think realistically be around on the ground floor as I'm retiring and it's starting up. I think faster than that is a pipe dream. That would be nice. I'd like that, and in an ideal world, I'd like to have enough, you know, intellectually challenging problems to solve along the way. Some of the, I don't have time to get into the details of it probably, but you know, some of the proposed facilities, if you're somebody who cares about processing data in real time, have bigger challenges associated with them than others. And of course, that's not a reason, that obviously is not a reason to build one facility or another, but it does mean that in some of them that for me personally is really within, you know, within the field, what I'm thinking about. And then of course I have, again, I have the freedom because of this my position, that I can think beyond necessarily collider physics. And I think there are definitely problems out there that haven't got much to do with collider physics that may be interesting to think about.
So what would you do if there was no collider physics? What would be the second best domain to study?
It's kind of funny. You know, I think, I mean, within physics itself, there are all kinds of things. There's the what's coming up, hopefully very soon, is a real chance to decide, to see whether there's matter-antimatter symmetry in neutrinos, which are a type of fundamental particle. One of the few types where we haven't nailed down whether it's there or not yet. That's definitely a super exciting problem. On the cosmology side, with gravitational waves, there's a whole range of exciting problems that have opened up. But there are also, you know, increasingly, and this is probably, you know, part of the heritage of being fundamentally a kind of, you know, East European dilettante intellectual in Paris. You know, there are fundamental kinds of, there are things where you also ask yourself, well, hang on, you're doing fundamental physics, but you're living in a country and on a continent where, as I kind of hinted at before, increasingly young people are unable to have affordable housing, reasonable affordable housing. Well, that's not a real problem. That's an entirely manufactured political problem. We are more than capable of building enough housing for everybody. We choose not to do it for a very complex set of reasons. Okay. And you can, and I've often played with my head with the idea of various econometric, simulations, if you want, of trying to demonstrate quantitatively, even though I don't believe it's actually a quantitative problem, why this is so ridiculous, and all kinds of things like that. But I'm probably in the early stages of a midlife crisis, so if you think, I mean, it's coming for me at some point, sooner rather than later. I mean, it's inevitable.
So you're thinking about working on the housing problem somehow, or the economy of it.
Let's put it this way: it's something that the absolute lack of logic in how things are organized today drives me up the wall every time I think about it, which is normally a good starting point for thinking, okay, I want to work on this.
Okay. Oh, that's an interesting one. Okay. Okay, maybe for another podcast. But the last question I want to ask is that I usually talk about this. As a scientist, it was never very easy to bring the science home because somehow, as I said, physics is so far away from what we do, but even computer science is so far away what we do at home when we hug our kids and we live there, And so talking about my science at home was always hard. Now you are in a position where this is not the case because your wife is also a physicist in the same experiment. So I want to ask you about that experience. Like, how is it? Does it make marriage easier that you work on the same thing, or harder?
Yeah, so that's a very interesting one. For the vast majority of our professional lives, surprisingly, but we succeeded in never working on the same thing. Or actually, we stayed almost as far away from each other within, what is possible within the collaboration in terms of our areas of interest. Kind of a bit of a family joke that I end up doing stuff that she did, but like 3 years later, which has happened a few times. But now that Yasmin is the physics coordinator experiment, it's been more complicated because well, actually on the organizational side, it's been very easy because I just no longer have any opinions, which is actually fine. About anything, because of course she has responsibilities for how certain things are organized, and it would not help anybody if I opened my mouth and said what I think about it. But on the physics side, I have physics opinions, and there it's not. There isn't actually it's not actually healthy for anybody to not express them, neither for me nor for her nor for, I'd like to think, for the collaboration. So there it's a bit more nuanced, but we work very, very hard to keep the evenings
physics less
as free of this. So I mean, it helps that our daughter is like 5 now. So at the stage, we're still at the stage where it's mathematics that's being introduced much more than physics. And of course, she's been to a control room. She knows daddy and mommy work on the experiment and so on. But beyond that, at dinner time, it can be factorized out. And I had, actually for most of right now, this year is the first time in like 12 years that I don't have a significant responsibility on the collaboration, which has been super liberating, because for most of my daughter's life, she got used to the fact that daddy's working very late at night, and now she has to get used to the fact that he's not, but mommy is, which is super confusing for her. But she's figured it out now. So she probably thinks there's now an oscillation effect. But
Okay, Vava. So maybe the last thing, if you want to ask me any question, you yourself.
um, yeah, actually, let me ask you, why the podcast? I mean, I'm actually, no, but I'm super curious because also because the way you frame the podcast, it isn't like a traditional, it isn't like a traditional podcast, but also, you know, and you get into topics from very like it's not the angles that you would like typically find, but I'm just curious, like at what point were you like, okay, this is what I need to put my energy into?
Hmm. Thank you very much. I mean, that's the question, actually. Well, it's complicated, but essentially, I got to be interested in somehow the border between spirituality and science. And this is where, all those blog posts that you mentioned come out of. Like, in science, we are looking for the truth, and then how do you decide which truth we want to look for? That's a profoundly non-scientific question, and the answers are also non-scientific. And I started to consume a lot of YouTube podcasts. There is a thing which is called This Little Corner of the Internet, which contains people from various sides of science, spirituality, religion, etc. And I felt that I had sort of like an urge to not only consume but also produce. I felt that there were a lot of things I wanted to say, and this seemed to be the easiest way to do this and the most fun way, actually, to interview people and see what comes out of them. I'm not going to, it's really hard to do this alone. I started to blog, but then I realized that the best way to actually talk about these things is a dialogue. And I also happen to have interesting discussions with people, in the office at lunch, and when I was at university, we had super interesting discussions with the students, with my colleagues, and I thought that this could be interesting to record. A lot of people are doing this, so why couldn't I? But the main reason was this sort of like this psychological urge to get my point of view out so people can see it, so I can get validation somehow of the thing that I'm interested in. It's a little bit like your housing thing. I It's not only anger, there is anger too. So if somebody contradicts you and you know that it's stupid and but there is also, that's actually the better type of emotion in this, because when you get angry, you argue with somebody that feels bad, but at least you are connected, right?
Yes,
But
definitely.
there is the other kind of sort of like cosmic loneliness, where you feel that what you have is doesn't interest anybody. And it's I mean, it depends on your psychological setup, but I have the tendency of believing that. So I thought, let's try it. I mean, a lot of people don't know me, don't know what I think, so let's try something there where these things can get out and can get built in a dialogical way. And so I was, cooking this decision for a long time, because it's not easy to start a podcast. I did two podcasts where I was interviewed, one by Paul van der Clay, who's a completely out of my domain, but he's a Calvinist pastor in Sacramento. The other one was by Karen Wong, who's also part of what we call this this little corner of the internet, who's a painter. And so we had very interesting conversations, and that gave me the taste so to actually do it by myself and actually maybe have my unique way of driving these conversations and participating in them. So I don't know where it will go. Right now you're number 4. So if it ever gets famous like Lex Friedman, then you will be on top of the list.
On the ground floor again.
Yes, but for now, it's I have very interesting people lined up, and I'm very, very excited to continue to do this. And honestly, after a while, you get into the routine. It's not that much of an effort, you know. To get into the, you know, to actually start it, I needed a lot of energy and generate dopamine from other sources. But once it starts, it sort of maintains itself. It's a really nice thing to do.
Yeah, I can. I mean, that part I can definitely see with the. You're very much into it. No, but I mean, this was because this for me was the first time. It's the first time that I've been interviewed in the podcast. But no, it was very. It was super cool and very interesting. Very interesting conversation, and I can see the motivation as well from your side. I mean, because I think because to some extent and maybe it is not true, but I think at least to some extent I understand the importance you place on the connection between science as a way of knowing things, but then the non-scientific aspects of deciding on what is important for you to know. And this is something which often gets reduced out of the conversation, or worse, you know, mocked as being, you know, irrelevant or even harmful. And that which I personally never subscribe to. So that's definitely,
yeah, they're definitely when I ask people why they do what they do, that can generate pretty varying emotions. Some people get angry. Some people get disconnected. That question doesn't occur to them. And the thing is, so this was, for me, this was like a daily question when I was the head of the Center for Data Science. A little bit what you described on like which systematic to devote time to, or which particle to devote the detector to. The setup of the center which was completely up to me, but the people around me, that we wanted to put AI into scientific pipelines, right? And Paris-Saclay is a huge university, so scientific pipeline, you have 10,000 of them. And among those 10,000, there was 100 who could like credibly ask for our help. And those varied from not between, you know, the Higgs boson and the B or whatever other particle, but between astrophysics, analytical chemistry, behavioral economy, and whatever, the Higgs boson. So I had to make decisions on which ones we pick up, and all of them were interesting intellectual problems. So that was the worst of it. So yeah, I couldn't use my general instinct of just going after the interesting problems because they were all interesting. And we had really finite resources. So I started to think about like how to formalize this decision process, and it inherently became political, not in the bad sense, but in the sense that these were value decisions.
Yes.
Which truth is more important? So this is where this whole thing started about now like 10 years ago.
But it's something that the field, and actually maybe that's a good point in some sense to emphasize, since we're wrapping up, is that this is something which you know, you see discussions on social media between people who are passionate about building the next generation of particle physics facilities and people who don't think it should be done. And something that I think we as a field actually struggle to engage properly with is, if you want to convince people, that typically you have to some extent to empathize with them. And it is often difficult to empathize and try to re-justify why this knowledge is what people should be sinking their time into compared to other knowledge. But at the same time, while often the argument is, oh well, it's not a zero-sum game, but when it comes to recruiting people and so on, it's not exactly zero-sum, but you are actually
close,
saying, well, you are saying, please invest your energy here. This is the knowledge that's worth your life to find. And that's something where the introspection, I think, is maybe not quite where it needs to be.
Yeah. And it's informal, it's soft, it's human, it's spiritual, it's about connections and the ambience in the collaboration and stuff like this.
Yeah.
Very much outside of the range of science. And so this is where this more global thinking of mine started, and then I got into this. It's meandering around the same way as you do in particle physics, right? So I can't really explain why I went in what direction, but what I'm really interested in now is to think about these questions, like to be very precise. The thing I'm asking in the blog is like, why did I work on the Higgs boson if I was an AI researcher who was dreaming about intelligence and cracking that nut? But somehow that, in 2014, I worked with Atlas and we did this Higgs boson challenge on Kaggle. Somehow it sucked me in. All those soft things that you're talking about, like actually experimental physics sucked me in, because I like so much the aspect of collaborating more. Especially in Auger. So I was in the Pierre-Auger collaboration, which is smaller. And it's really like the sort of like the wild west of experimental physics,
I remember your stories about Auger.
And it was about the Dunbar number of people in the workshops. So it was really like a warm, cozy place to be. And I sort of forgot about my dreams of, working on intelligence or artificial intelligence. And it lasted for a while, and then I started to ask these questions, and then I came out of it actually and went back to AI. But the question lingered, like, why do we do what we do? And what is my real calling? Because this is something mystical, like I can't answer either why. And this podcast was just somehow the natural choice at a certain point, and we'll see where it will go. But for now, I'll do the first season for sure for this year.
Well, okay. It's been a pleasure, really.
Yeah, it's been a pleasure, and thank you very much for this last question, and thank you very much for all your answers. It was super interesting. I have like tons of more questions and more precise details, and also about the sociology of the collaborations, but maybe another time.
Absolutely.
So thank you very much, Vava, and actually see you tomorrow for the goulash.
Definitely.
Bye bye.